Right. You ready to get mind blown? This usually blows people's minds. No, you're not yet. You're not. I can tell you're not. Let's do this one first. I won't blow your mind yet. Let's do this. I still have time? Yeah, plenty of time. All right, so I don't know if you've ever wondered this. I'm sure that you have. I'm sure that you've been sitting there probably, I don't know, out with your friends. And you've been sitting there thinking about the sine function, right? You're just like, you know, you're like, man, that sine function is something else. And you say to yourself, you know, I've always wondered what the area underneath one of those arcs of sine is. Don't lie, you know you have, right? I wonder what the area of that arc of that sine, that's what we call that. That's just an arc of the sine, not arc sine, but it's one arc of the sine function. What is its area? I'm curious, aren't you? Well, what would we do? We would set up a definite integral. I've really got to go to the restroom, I'm sorry. Y'all set that integral up and see if you can. What is it? What is it? 2? I unmuted it. Yeah.
Hey, is it 0? Shit.
Is it? Did you just do one arc? Just this arc? All right. Did the formula break? Okay, so what are we integrating? What's the integrand? Sine x. Okay. Sine x dx. What are the limits of integration? What's the lower limit? 0. What's the upper limit? Pi. Okay. Did everyone use pi? This is pi, right? Okay. So now, what's the antiderivative of sine? Negative cosine of x. I don't do plus c because I'm doing a definite integral. I put this line here. That reminds me I still need to plug in those two values, right? Now that's going to be equal to something minus something, right? First I plug in what? Pi. So this is negative cosine of pi. And then I'm going to plug in 0, so negative cosine of 0. Now cosine of pi, you need to know what that is. So you got to go and think about your unit circle. Cosine is the x-coordinate. And if you go to pi, you're over here, and the x-coordinate here is -1, right? So that's going to be negative -1. So that gives you 1. And then minus, let's see, cosine of 0 is 1, because now you're here. So this is minus -1. So plus 1. So the area is what? 2. Is that not weird? Is that not weird that you have this very strange shape, right? And your area turns out to be a nice integer, 2? It's weird, right? Yeah, but isn't that kind of strange? I've always thought that's strange. I mean, look, you're going from 0 to pi. Pi is an irrational number. That's this weird number. And somehow, this crazy curved shape, when you add up all the area in there, you get 2. Okay, that's what it is. All right, now, what would happen if I said, look, let's include this area here? Are we going to get 4? No, what are we going to get? We're going to get 0. Now that's just weird, okay? 0, now this time if we went the whole way, from here all the way to the end, we're going to go all the way to 2 pi this time, right? Same integrand, same antiderivative, just different limits of integration. But this time when we plug in, we go negative cosine of 2 pi, and then we go negative cosine of 0. 2 pi and 0 are at the same place, aren't they? So whatever this is, we're subtracting it. So it goes away. What does that tell us about this definite integral? What does it tell us about how it handles the area above the x-axis and below the x-axis? It's going to treat this area as a positive number, and that means it's treating this area as a negative number. That's weird, right? Because isn't area always positive? Well, here's why this happens. Remember when we're doing our rectangles in here? The height of the rectangle is the function's value there. So if I plug in a point here and I spits out that answer, that's going to be a positive number. So I'm going to do the width, which is positive, times the positive height, that's positive. But if I do a rectangle down here, like that, when I plug in this endpoint and I find the height, it's going to spit out a negative number. The width is still positive, so when you multiply those two, you get a negative. And when you add them all up, they're negative. So this is an important characteristic of the definite integral. Areas that are above the x-axis are counted as positive, and areas that are below the x-axis are counted as negative. So if you take an integral, and let's say you go from 0 to 10 of some function, and you get 0 as an answer, that usually means that either the function is just flat, like just on the x-axis, just the whole time, there's no area ever, or some of it's going up, some of it's going down, and they're offsetting each other, right? They're canceling each other out. Okay. Is it the same with cosine in terms of, do you get? Like that area is 0? The total area would, yes. So, but we're talking about you're talking about one period of cosine, right? So cosine looks like this, right? That's cosine. So if you were to integrate from here to here, this right here would have an area of 2. I'm sorry, negative 2. And then this right here, from here to here, that should be 1, and this one should be 1 also. And so this part and this part are offset by this part. Now you could check it, right? Like you could just integrate cosine. How hard would that be? Integral 0 to 2 pi, integrate cosine, right? What's the antiderivative of cosine? Sine x, 0 to 2 pi. At this point, you plug in 2 pi, sine of 2 pi, minus sine of 0, right? Sine of 2 pi is 0, minus 0, 0, so you get 0. So yes, they do cancel each other out. All right, time for us to have some fun. So we're now armed with this very powerful theorem, and let's go after the problem that the Chinese exhausted themselves on. All right? You ready to go after it? Area of a circle. Okay, here we go. First of all, let's start by drawing a circle. And this circle that we're going to draw is going to be centered at the origin, and it's going to have an arbitrary radius. And that arbitrary radius I'd like to call capital R. Is that all right with you? Capital R. That's the radius of this. So this right here is capital R, like that from here to here and from there to there, right? Now, do we know the equation of a circle centered at the origin with the radius of capital R? This you have to remember from pre-cal. I'll put it up here, see if it looks familiar to you. Does that look familiar? I'm using this formula right here, x minus h squared plus y minus k squared equals r squared. That's the general formula for any circle centered at the point hk with a radius of r. So in this case, our center is the point 0, 0. So that's 0 and that's 0, so that gives us x squared plus y squared, and then our radius is capital R. Okay, so that's something we have to know from before. So we all agree that that's the formula for it? All right, I'd like for us to find the area of that. So here's what we're going to do. We're actually just going to look at this piece right here. And we are just going to look at the area of that 1/4 of the circle. All right? So what I need to do is set up a definite integral. And I'm going to be drawing rectangles in here, right? Well, I'm not going to really, but that's what this is going to be doing, drawing all these rectangles in here. So can you tell me what A and B are for us here? I'm going to go 0 to where? Capital R, right? This definite integral is going to go from 0 to capital R. Now the important part is to figure out what the heck is the function, right? What is the function? We've done sine, we did sine, we did cosine, we did x squared, but what is this function? So how could you get that function? What would you do to get it? That is the area, 1/4 pi r squared, but you're cheating because you're using a formula that we're acting like we don't know, right? We're actually going to come up with that formula. What I'm saying is, what is this curve? What is the function? What is that function? Well, look, this is our relationship, right? That's it right there. That's the relationship between the x and y coordinates. So can you solve this? Can you solve this for y? Okay, how would you solve that for y? You would take x squared to the other side, right? Right? And then you take the square root. So you get y is equal to, and then when you take the square root, you have to do plus or minus. Square root of capital R squared minus x squared. Yeah? All right. Now, if I do the plus and not the minus, and I graph this, it actually gives me the top half of the circle. If I do the minus and not the plus, it gives me the bottom half of the circle. And the reason is because a circle is not a function. It fails the vertical line test. So if we solve for y, we're going to have actually two pieces, the top piece and the bottom piece. So I am going to only use the plus here because I'm talking about the top part, right? So are y'all okay with the idea that our function in here is the positive square root of capital R squared minus x squared dx? Are you okay with that? You sure? Now R here is a number, right? Capital R? It's a number, but we're not saying what it is. But we are assuming it is some fixed number. Someone's giving us a radius, right? So can you integrate the square root of something squared minus something squared? A sine theta, right? This is a trigonometric substitution. Now we're kind of squinting our eyes and saying, hey, that's a squared, right? A squared minus x squared. So I'm going to make a trig sub now. x is going to be, now a sine theta for us is really what? Capital R sine theta, right? And then the square root of r squared minus x squared, we already know using this trig sub thing that this turns out to be what? R cosine theta. And then dx, well, what's dx? R cosine theta d theta, right? So this is all just trig sub. Let's rewrite the integral. Or actually, yeah, I'll rewrite the integral.
So
that's trigonometric substitution, 6.3, section 6.3. I'm doing basically trig substitution on this, but instead of a squared, I'm using r squared. So this is the same formula. Okay, what the heck am I doing? Oh, I'm rewriting the integral. So let me just, I'm going to come back to this because that's my definite integral. I'm just going to be looking at the indefinite integral first. Right, so notice I don't have my limits of integration right now. If I rewrite this, what does this become? According to this, it's what? R cosine theta. That's this root part. Then dx is what? Capital R cosine theta d theta, right? Oh, are you happy to see that? Yeah, because that's going to be cosine squared. And we can take out r squared, because capital R, that's a constant. So this is capital R squared integral cosine squared theta d theta. And how do we handle cosine squared? Yeah, there you go. It's the power reducing one, right? So this is going to become that 1/2, blah, blah, blah. I'm going to bring the 1/2 out. And then, wasn't it 1 plus cosine 2 theta? I think we did that quite a bit, didn't we? We've seen that, that thing a few times now. It's made an appearance. Okay, what's the antiderivative of that? So no more integral sign. Antiderivative is theta plus, yep, 1/2 sine 2 theta, right? Plus a constant. Now, I realize I'm not going to need that constant over here, right? But are y'all all right with that so far? Now, we've done this several times, right? Sine 2 theta, double angle identity, that's 2 sine theta cosine theta. So this becomes 1/2 capital R squared. We've got theta. We've got what here? Just sine theta cosine theta. Good. Plus c. Right? Because the 1/2? Okay. All right, now we have to get everything from theta back to x. Triangle, right? So let's do this. I'm so excited for you all right now. Okay, so let's see here. I'm using this piece of information right here, right? So according to that piece of information, I know that sine theta is x over capital R. And that means that theta is arc sine of x over capital R. Agreed or not? That's just me moving the R over and then taking arc sine on both sides. That's what theta is. So I've got that to be able to replace it. And then this right here I'm going to need the triangle for. Using this information, theta, sine is opposite over hypotenuse, which means our adjacent side is root capital R squared minus x squared. We're really close right now to having this. You all ready to rewrite the integral? Okay, so look what's going to happen now. I'm going to come back to this now, all right? I'm going to come back to this. Okay, let me rewrite it because I need some room. The integral from 0 to capital R of square root of r squared minus x squared dx is equal to the antiderivative. Here it is. Here it is. 1/2 r squared And then what was theta? Arc sine of x over r. And then plus sine theta, x over r, times cosine theta, which is root r squared minus x squared over what? R again. Okay, that's my antiderivative, right? But I need to evaluate it where and where? 0 and capital R. Right? So this equals, all right, here it is, man. This is going to be so freaking great. Okay, here we go. We are going to first plug in capital R, right? Are there any questions on how I got to this? Because, I mean, we're about to prove that the area of a circle is pi r squared. I want to make sure everyone's with me here. Yes? Capital R goes in for what? What am I replacing with capital R? The x's, right? The x's. So I have 1/2 r squared. Okay, now, arc sine of capital R over capital R, which is 1. Okay, plus capital R over capital R, right? 1 times, now check this one out. R squared minus R squared. 0, 0, 0, right? That's just 0. So this is actually, this term is dead, isn't it? Nice. All right, so I've plugged in capital R. I need to close my brackets. Now I need to subtract from that whatever I get when I plug in 0 for x. So I rewrite everything. 1/2 capital R squared, brackets. Okay, 0 goes in right here. 0 over R, 0. So arc sine of 0. And then plus, now 0 goes in for x, right there. 0 over R, that's all 0, isn't it? It's all gone. You can taste it. All right, so here's where we are. 1/2 capital R squared times arc sine of 1. That's that. Minus 1/2 capital R squared times arc sine of 0. That's this part. I forgot my bracket here again. Let's go back and let's try and remember what the heck arc sine means, right? This is saying, hey, look, somewhere on your unit circle, there is an angle that corresponds to your y coordinate. Why am I talking about y coordinate? Because it's sine, right? Arc sine. So where on your unit circle, at what angle is your y coordinate 1? Pi over 2. So this is pi over 2. 1/2 r squared times pi over 2 minus, now arc sine of 0 is saying at what angle is your y coordinate 0? Here, right? Why not over here? Domain restrictions on arc sine. Domain restrictions on arc sine. You can't look over here, right? Arc sine, you can only look in the, well, between negative pi over 2 and pi over 2. So we have to be at an angle of 0 here. So this is 0, which kills everything over here. And so our final answer is what? Pi r squared, I'll write it that way, over 4. Right, we're multiplying 2 times 2 is 4, right? Wait a minute, I thought the area of a circle was pi r squared. We only found that area. Times 4 is the area, right? So that is the area of that one piece. If we multiply it times 4, that should be the area of the whole circle. So this times 4 is going to give us pi capital R squared. There it is. That's how you prove that the area of a circle is pi r squared. So poor Chinese and many people after that were trying to find the area of a circle. And it was after calculus that we were able to get it. We needed it, though. We needed the calculus. All right, well, let's see. What can you do for homework? Nothing, right? We can just take the day off. Who has the, like, I have the list, but it doesn't have the homework assignments. Do you have something for 5-4 in your homework, on your homework list? Can I see yours real quick? Ah, okay. So I guess I'm going to announce it now.
It's 5.2, 5.3, and 5.4. Evaluating definite.
Yeah, but look at the homework assignment. There's nothing there.
Yeah, and then like the latter half of it is also empty.
Yeah. All right, I would like for you to, for homework, I don't think I have videos on this homework set. Could be wrong, but I don't think I have videos on this. I'd like for you to look at 5.3. This is for homework. And I'd like, that is page 289. And let's just try and do, 1 through 21 odds. So you can check your answers in the back of the book. All of those are definite integrals. So they give you an integral, they give you the limits of integration, and you plug in. So here's the good news. This is Chapter 5, Section 3. Chapter 6 was where we learned all the techniques of integration. That means that every one of these problems that are here are going to be some basic integral. It's going to be power rule or something. So this is really just practice, all right? If you wanted to, what you could do is you could go back, and you know how in the sections for homework that you did before, I said ignore those numbers? You could go back and look at your answer and just plug in the two numbers and see if you can get the answer to match the back of the book. Because really, that's all this is. We're adding one more element onto it now, right? We're just at the end plugging in two numbers and subtracting. Y'all look ready to go. I know you're ready to go. All right, go. That's fine. Everyone's turned in their thing, right? It was due at the beginning of class. Uh-oh, this one's not stapled.
Yeah, I had one paper.
No, this is someone else.
I have a staple.
Way to throw him under the bus.
There's a guy selling staples for $20.
I say, way to throw him under the bus.
Please, yeah. Is yours not, that one's not stapled? Yeah, can you staple that, please? All right. All right, everybody have a good weekend. I'm going to do it off of the take-home thing. Yeah.